Hello, welcome back to another video about inverse functions. In this video, we're going to study the graphs of functions and their inverse functions. Alright, but as we always do, we have to return to basic principles and then make our way out. For today's video, we're going to be using this function here, and we're going to find its inverse, graph them, and then study the graphs. Alright, let's find the inverse. Well, that's pretty easy. Let's solve for x in terms of y. Let's subtract 9 from both sides. The 9's on the right hand side will be 0, they cancel out. And then let's divide both sides by 3. The 3's cancel out. 3 divided by 3 is just 1. And then we can simplify the left hand side. So y over 3 could be 1/3 y, and 9 over 3 is just 3. So we get the following equation. Now, for the final step, we can switch the x and y variables. Why is that? Well, that's because an inverse function is a function in itself. It's just another function. So we could just switch these variables, and then now we could call this f inverse. F inverse, the inverse function of the function above, is equal to 1/3 x minus 3. Now, before we move on even more, let's consider the mapping diagram here. For example, a mapping diagram of a random function. I didn't write the function out, but let's study this. It maps inputs to outputs. That's what the function does. Great. Mapping 1 to 3, 2 to 4, 3 to 5. Inputs to outputs. Great. This is just notation, which is really good to use when dealing with mapping diagrams. Now, what does an inverse function do? Well, we know the answer. The reverse operation. Instead of going from the inputs to the outputs, it goes the other way, basically going from outputs to inputs. So instead of going from 1, which is an input, to 3, an output, the inverse function, f inverse, would go from 3 to 1, the other way. And the same applies to the other pairs of numbers. Great. Now, let's write these pairs as ordered pairs, because we're going to be dealing with graphs soon. So let's deal with these pairs as ordered pairs. For this random function, from its mapping diagram here, for a few set of points that we have here, let's write out ordered pairs. And we know an ordered pair is just an input-output pair, an xy pair, coordinates, which we use to essentially graph. So for this function, we could write the input-output pairs, or the ordered pairs, as a set. So it has this set of ordered pairs. So this random function, from its mapping diagram, has the following set of ordered pairs. 1 is paired with 3, 2 with 4, 3 with 5. You notice, input is the x value, output is the y value, and they're paired through their mapping, and they're paired together. Alright, how about the inverse function? Well, it always does the opposite. So we're going to write f inverse has the following ordered pairs. The inverse function of this mapping diagram, or this function we're dealing with, would have ordered pairs of 3, 1, 4, 2, 5, 3. Why is that? Well, notice, again, inverse functions take us from the outputs to the inputs. They take in outputs and give us inputs. And so we could say that the inputs to an inverse function are the outputs of the original function. Notice, the outputs of the original function are the inputs to this inverse function. 3 is an output of the original function, which is now an input, an x value for this inverse function, and the same goes with the rest. And the outputs are the outputs of the inverse function are the inputs in the original function. Notice we have 1, 2, 3 as the outputs in the y values in the inverse function, which are in fact the inputs in the original function f. So we can also see here that what we're basically doing is flipping the ordered pairs. So the inverse function has, for example, an ordered pair of 1, 3. So the original function has this ordered pair 1, 3, for example, while in the inverse, it's flipped. It's 3, 1, as a result of the reasons I've just explained. But notice, it's just flipping. That's what we're doing. So we could say, instead of xy, which is applied to normal functions, when we compare it for the inverse function of a function, we just flip those pairs. We flip the x and y values in an ordered pair. That's basically what's happening from a normal function to an inverse function. Now let's get into the graphs. Let's draw our xy plane here, and our linear function y is equal to 3x plus 9, which is also our so-called original function. What are the key parts of this graph? The intercepts. It has a y-intercept of 9 and an x-intercept of -3. Now, let's draw the inverse function. Here in green, f inverse is 1/3 x minus 3. That's the inverse function. The key parts are the intercepts. Again, the x-intercept is 9 and the y-intercept is -3 for the inverse function. Okay, so we have our graph here, our original function in red and our inverse function in green. Okay, so now to notice what's happening here, let's look at random points. Maybe pick the intercepts. They're easy to work with. The x and y intercepts for each function. So for the original function, the y-intercept is 9 and the x-intercept is -3. For the inverse function, the x-intercept is 9 and the y-intercept is -3. Let's write these out in terms of ordered pairs. So for the original function, f of x, the x-intercept, we would write the coordinates or the point as follows. X-intercept is -3, 0, and the y-intercept would be 0, 9. Okay, now, so this is for the original function. Now, the inverse function, I'll write down below. For the inverse function, f inverse, the x-intercept would be 9, 0, and the y-intercept would be 0, -3. What do we notice here? We notice similar numbers. We notice 9, 9, 0, 0, -3, 0, 0, -3. What about these numbers? Well, if you look closely, the points or the inputs and outputs are flipped. The x and y are switched, going from the original function to the inverse function. Notice, we have this set of ordered pairs, -3, 0, 0, 9 for the original function, and in the inverse function it's flipped. The 0, 9 becomes 9, 0, the -3, 0 becomes 0, -3. The x and y are switched. They're switched. That's what I've explained in the previous clip. From x and y we go to y comma x in the inverse function. Why is that? Well, it's again, instead of going from inputs to outputs, inverse functions take us from the outputs to the inputs. So the output, 0, if we look closely, becomes the input down here for the point on the inverse function. Outputs are now inputs in the inverse function. You could even see that in the graph over here. Let's have a look at the graph. 0, 9 is the point over here. 9, 0 is the point over here. -3, 0 is the point over here. 0, -3 is the point over here. On the original function, -3, 0. But when we go to the green, the inverse function, it's flipped. The x's are now the y's. The x of the original function is now the y of the inverse function. Basically, the inputs, the outputs of the original function, for example 9, are now the inputs of the inverse function. Things are being flipped. Outputs are now inputs for the inverse function. Again, I repeat. Outputs are now inputs for the inverse function. Now the main point of all this is that the graph of the inverse function is a reflection over a specific line. Y is equal to x. If we draw that line over here, that line y is equal to x, we see it creates a reflection. The inverse function is a reflection of the original function over this line, y is equal to x. Because notice, this point here, 0, 9, is being reflected across this y is equal to x line of symmetry. And here the point is now 9, 0. If we go to the x-intercepts, we notice -3, 0 is reflected, basically, and is now 0, -3. Again, the flipping scenario, which results in this symmetry and reflection. This holds for all points. You can test it out yourself for all points. So we can conclude that the inverse function, any inverse function, okay, its graph is the reflection of the original function over this line of symmetry, y is equal to x. Great, so that's how it works. I'll see you in the next one. My email is down below. Send me anything math related.